English as Moshe Vardi. Now it's kind of like, we really need to introduce Moshe Vardi to this audience. Okay, so I see nothing but no. So I guess you all know him. You know all about his work. You also know about. Let me try to see what I know that. So, but maybe let me give you something that, like you all know that about his results in synthesis, formal methods, verification. This is what is well known. But also, I want to thank him that about all the work that he did as an organizer here. You know, like you would assume that he was, you know, like, I'm Moshe Vardi, I don't need to do anything. That's really not. He was the really like driving force. Like me, on the Saturday night, we would have a course where we would actually go through each and every participant. And I really want to thank you, Moshe, for everything that you've done to make this workshop happen. So, and also thank you for all the work. So let's kind of hear more about synthesis now. But so thank you particularly for this workshop.
Thank you, Rosika. I'm going to kind of tell you where I've been, where my attention have been on synthesis over the past few years, but I'll start just to put us all on the same, I think the first few slides everybody will know, but just to put us all on the same vocabulary. So we're looking at reactive system. These are systems that interact with their environment, or you call it open systems. The first reactive system is from an important paper by Amir Pnueli from 1985. And you know, originally people were thinking about like hardware, circuits, and operating system, connection protocol. More recently, robots, and I'll come back to robots because even the focus on robots will change somewhat how we are looking at things. Okay, but here is the classical one: is to build a printer driver, and so you have jobs are submitted and they are printed, and you don't want to print two jobs at the same time, and every job submitted should be eventually printed. Something very, very simple. And the idea was that we need to look, because we're looking at systems that continually interact with their environment, we're looking at infinite behaviors. The printer driver should work forever, so we assume that it has infinite lifetime. And that probably goes back to Church, when he introduced actually synthesis for monadic second-order logic. He said, let's see, you know, he was looking at circuits and said they have to run forever. It was very important. But the shift on focus is important because the Manna and Wolninger was about programs that have input translated to output. And now we have this input and output pairs that go on forever. It's an ongoing interaction. So that was a shift on focus. I said, it started in Church. But it got a big push when Amir Pnueli introduced linear temporal logic, or introduced it to computer science. It really came from philosophical logic. But it was developed already in the 1950s by Pryor that tried to think about how people use time in natural language. And we don't use explicit time coordinates for most things. We use relative time coordinates. We said tomorrow, next week, next year. You know, we talk about the program tomorrow, and nobody said on July 2nd, right? We said tomorrow. And so this was the language introduced by Church, and then Pnueli brought it to computer science. And it's a logic of temporal sequences where you take propositional logic, but now you have infinite sequence of truth assignments, and you could talk about what will happen the next time clock, what will happen is eventually, and things like that. And this is all discrete time. The whole other issue, what happens if you go continuous time, and I will not talk about it at all. So the idea of temporal realizability, again, I'm going to use the more modern terminology, but this, in some sense, this all goes back to Church, is that you talk about interaction between the system and its environment. So the system receives inputs from the environment and issues back outputs to the environment. And we're going to think about it as a game where at each, and we will assume that they are playing at the same time. There are all kinds of variation. Who moves first? We will talk about the move at the same time. And the system chooses an output assignment, and the environment chooses an input assignment. So the play is a sequence of such pairs of input-output assignments, and that's our trace. And we're going to have we're going to specify the behavior over this infinite trace using LTL or MSO. And the question is, and that again goes back to Church, but was kind of rediscovered by computer scientists in the late 80s, which was about does the system have a winning strategy? And that's a function from all the input has seen so far to the next output. So you have, in principle, unbounded memory. And in reality, we find out we don't need unbounded memory, but you need to be able to make the decision on the next move based on everything happened so far. And about the same time, independently, Vardi, Lamport, and Wolper, and Pnueli and Rosner says that the important thing is there a winning strategy, and that's called realizability. Is the specification realizable? Is there a winning strategy? And in terminology of AI, this is called a universal plan. I mean, classical AI planning was just, there is a Shaky the robot, and Shaky the robot wants to be able to walk and get out the door. And there's no environment to interact with. But here, there's unpredictable environment. We don't know what the environment will do. And you have to deal with all possible contingencies. So that's called universal plan. And the idea is if you want autonomy, then you know that things will happen and you have to deal with them. So Rabin introduced the idea of tree automata. And what is an infinite tree? So we have a set of direction. You can think of it left and right, but in general, if you have a set of direction, and the tree is simply D star, which is all the possible, all the worlds over D. And if you have a child, and XD is also if you have a node X and XD is the child. And the label infinite tree is when you put a label at every node of the tree. And Rabin said, wait a minute, strategy is a mapping from 2 to the I star to 2 to the O. It's a tree. It's a tree labeled by input assignment, a tree where you branch by input assignment, and the labels are output assignment. And so once you think about the tree, you can develop the machinery of tree automata. Now, Rabin did not introduce tree automata. They were introduced a few years before him on finite trees. But he said we can also develop this on infinite trees. And so, so now the question is, you build the appropriate, I won't get into the detail, you build the appropriate automaton that accepts all winning strategies. And now you ask, is it empty or not? If it's empty, unrealizable, it's not empty, it's realizable. And the earlier work was emptiness of automata on finite trees, and that's in polynomial time, affecting linear time. Infinite trees, it's a whole different stories. In fact, it took many, many years before we understood fully their complexity. First, it was a Rabin algorithm was non-elementary, reduced to 2x time, eventually x time, eventually the NP, and eventually it was settled to be NP complete. So if P is equal NP, then we see a clear difference in complexity between finite trees and infinite trees. That's an important difference. So this is Rabin's algorithm. You're given an LTL formula phi that describe the requirements from your system. And you have to construct a Rabin tree automaton, except all winning strategy for this specification. You check for non-emptiness. And if it's non-empty, the realizability algorithm produce witnesses for the non-emptiness. And from that witness, you can extract actually the strategy itself. So in some sense, the algorithm does both. It gives you realizability, but the evidence that it produces in the computation give you the strategy. And one of the things that does follow, even for MSO, if there is a strategy, there's always a finite set strategy. So even though you need to remember the full history, you can do it using finite amount of memory, okay? Now, the complexity that remember, Rabin non-emptiness algorithm was non-elementary. But Rabin said that's not a problem because it was already a non-elementary to construct the automaton. So if we have non-elementary, just still non-elementary. What's the big deal? Okay. So to go from MSO to automata, that's already non-elementary. Every quantifier implies an exponential blow-up. So they were happy to live with non-elementary. We'll come back to that point. Now, in some sense, I would say kind of the basic mathematical framework was all laid out by the time we reach Rabin. And everything that happens after Rabin all has to do with scalability, performance, complexity, okay? The basic machinery was laid out before. So first, Pnueli said, instead of using MSO, let's use LTL. Now, it's very clear that LTL is a fragment of MSO. It's also very, very easy to see that LTL is weaker than MSO. But so why use LTL rather than MSO? It's a more natural language. It's a more natural language that people do express properties in a very natural way, like, P until Q, P will be true until Q is full. You can write it MSO, it's much more cumbersome. So in terms of usability, LTL was a better language. There was an issue of expressive power, but I won't address it here. But Pnueli, when he talked, for example, about verification for LTL, he still talked about you have to convert it to MSO, because that's the way you can do verification using automata. And then in 1983, Pierre Wolper and I showed that there is an elementary translation from LTL to automata. Elementary just means one exponential. Normally we talk about exponential blow up, but here, hey, we started from a tower of unbounded tower of exponential. One exponential it's exponential blow down, I'll call it. Still, going to tree automata was a bit more complicated, but then we had the important contribution using Safra with a new determinization construction, and now we had a double exponential construction of tree automata. And once that happens, once you have the double exponential construction, from this would follow a Pnueli and Rosner proof that it gives a 2x time upper bound. And Rosner in his dissertation showed that you can also show a matching lower bound. So by 1990, we understood the theoretical problem 2x time. Now, 2x time is a horrible complexity, okay? I mean, just take doesn't take much, 2 to the 2 to the 10. I mean, these are horrible numbers. So why are we here if it's 2x time complete? Well, because it's worst case complexity. And in a worst case, a meteor is going to hit this room, this building, before the end of the day, and we're all dead, okay? And still many of you have spent money to buy a return ticket, okay? In fact, it's even worse, talk about worst case complexity. If you take a car ride for 100 miles, what's your risk of getting killed on the way? Anybody knows? 1 in a million. What's that? Depending how you drive, yes. 1 in a million on the average. And nobody thinks twice before they go into the car and they drive 100 miles, okay? It's 1 in a million. So the answer is we ignore certain things. We say, okay, it can happen, but I was a bit surprised, 1 in a million. I thought 1 in a billion, okay, I'll ignore, but the reality is we ignore even 1 in a million. In fact, I had an interesting experience. I asked ChatGPT some time ago, there was some discussion about uncertain quantification. So I asked ChatGPT, what is the probability that the Rice administration building will collapse the next day? And ChatGPT came and says, 1 in a million. And so we said, how did you come up with this? It says, oh, it's just a low probability. So 2x time, in fact, 2x time also mean that in some cases, the smallest strategy is going to be of double exponential size. So clearly there are convoluted specifications that, yes, it's realizable in theory, but not in practice. But what will happen in practice? So the issue is, okay, we have other problems that are hard, but we still solve them in practice. So much to do about practical complexity, and that's not a very well-defined notion, very much a research topic. But the answer is, even without the 2x time, the algorithmics in here of this problem has been very challenging. So let's dig in a little bit. So we have, when we go from LTL, we go to Bushy automata, which are essentially take non-deterministic automata, but let them run forever. Instead of running on a finite world, they run infinite world. And to accept, you don't end them in an accepting state, but you have to visit an accepting state infinitely often. And that was due to Bushy in around early 1960, I think, first. And this Bushy automata started the whole idea of formal language theory over omega words rather than on finite words, and automata on infinite words. And one of the things that we do know that these automata are as expressive as MSO, because that's what Bushy has shown, that you can translate from MSO to his automata. Later on, we call them Bushy automata, and they're even more expressive than LTL. And again, we can go from MSO, but that will involve an elementary blow-up. But the key result of Vardi Wolper in '83 was that there is a translation that does not go through MSO, and it's only exponential. Okay, and it's a I call it the compilation theorem because it's you can start from declarative. LTL is declarative, and I think of automata as an imperative formalism. So there is a compilation, and there is at most one exponential blow-up. And that's kind of a very important paradigm. It's an example, a very important paradigm in computer science to go from declarative high-level specification to imperative low-level specification, one of the most important ideas in computer science. So this gives us a rise to what I would call realizability game. And now we can go to the more abstract way of looking at it. So imagine we have two alphabets, one for the system, one for the environment. And each round, the system chooses a letter and environment chooses a letter. So we get a pair of letters. And the infinite play is going to be a pair of words, an infinite sequence of pairs of letters. So an infinite word over sigma cross delta. And we have a Bushy automaton that describe good behaviors. And the system goal is to be able to play forever and end up, regardless what the environment will do, you should get a play that is accepted by the automaton. Now, if you try to solve it, then you run into the problem of the following, that non-deterministic automata have foresight. That is, they get to choose the run as if they have seen the whole words. Even it's an infinite world. They stand up there, they see from here to eternity, and they say, okay, now I know what to do. But in life, we don't have this luxury. Programs don't have this luxury to know what is going to happen. And so non-deterministic have foresight, such as do not have foresight. The only way we know how to do this, well, not the only way, but the main way we have how to do it is determine as A. And that has become of exactly what do we need from this automata to be able to do it, the whole concept of good for games that can we do with a little less determinization, but I won't go there. So we determinize A, and then we are running into another problem, which is not so easy. Unlike automata on finite words, which are relatively easy to determine, just subset construction. First of all, unlike what we have in automata on finite words, the non-determinism does not add expressive power. This is not the case for Bushy automata. Non-determinism does add expressive power. And the canonical example due to Landweber was you want to have a tail of ones. So how do you check that you have a tail of ones? You just have to make a decision. From now on, it's going to be only ones. But there's no way, you need foresight for that. There's no way to deterministically to say from now on it's only going to be one. And then McNaughton finally came up with determinization. Very non-trivial paper. Not easy to read. Explain how to determinize Bushy automata using a more general acceptance condition. I won't get into the details here. And it was doubly exponential. Determinization was doubly exponential. It took a while to realize that. I remember meeting McNaughton and asking him about whether he thought about the blow-up of his construction. He said, lots of states. But he said it twice. And I think that meant doubly exponential. Lots of state, doubly exponential. Now, the acceptance conditions were, to go beyond Buki was a matter of research, and eventually we kind of converged on the concept of parity automata, which is not a trivial notion. You kind of look at it and you say, where did this come from? And the only answer is you had to be there, kind of emerge out of exploration. But here you have a partition of the set of states, so you have a tuple of sets of states, and K is called the parity index. And the acceptance condition was that because you cover the whole state space there, it means that one of the sets must be visited infinitely often, right? Pigeonhole principle. pigeon hole principle says if you put infinitely many pigeons, infinitely many holes, one hole will have infinitely many pigeons. So the least Fi that is with infinitely often should be even. I remember talking to people who do combinatorial game theory, was a research area, and telling them about this game. And they look at like, why would you want to solve this game? It's just a weird, unnatural game. Why would you want to solve it? But Safra has shown that you can take a Bush automaton with n state, and you translate it into deterministic parity automaton with exponential blow-up in the number of states, but only a linear parity index. And that's very, very important, linear parity index, because the parity index goes to the exponent. So if the parity index has been exponential, we will have double exponential complexity. This way we only have n to the n squared, which is not a very nice number, but at least it's only single exponential. So this gives rise to a certain to a game that has been a central object in the theory of temporal synthesis, which are parity game, where you have this in the abstract way, you have a graph, and it's a bipartite graph, and two players move a token between V0 and V1, and again along the edges of the graph, and again you have a partition of the state space into states, and that's the parity index, and the player 0 win if the least Wi, if the least H Wi with infinite often is even. And this is still an open question. Is it in polynomial time or not? We know it's in quasi-polynomial time, which is 2 to the polylog of n, but we still don't know whether this is in polynomial time. And at the same time, there's lots of work on good algorithm. Good means good in practice algorithm for this problem. So this is now the story of LTL synthesis. You start from your formula phi, you construct a Bush automaton, you convert it to a deterministic parity automaton, you solve the parity game. This is the canonical approach, and it's 2x time. And out of this, you get also synthesis. You get from this a transducer, which is a finite set program with exponentially many states. I'm sorry, with double exponentially many states. Again, not a very nice result. Now, you think, okay, maybe this double exponential time would be the end of it. But in reality, people have shown that that's not necessarily the barrier. You know, Mona has been a successful package for dealing with MSO on finite world, which is non-elementary. In the worst case, we're all dead. And we don't worry about complexity. So what happens in practice? This is a real question. The same story was about LTL, model checking. It's space complete, which typically we think of again as a hard, and we do it in practice. And there have been other successes of the automata theoretic approach in different contexts. So if we decided we're willing to live with what's complexity, if we can solve practical cases, then we can move on. But still, LTL synthesis proved to be just a very difficult challenge. Why? Because terminization is still hard. I mean, I love this example. You start from 9 states, Bush automaton, and you terminize, and you get million states. And it's not the most elegant construction, and parity game are still difficult. There's still some progress here, but it's just still a very, very challenging problem. And there have been one kind of success there, which is, let's not deal with full LTL. Let's look at a family of expressive specification, but not as expressive as LTL. And this is GR1, and it's just implications of infinitely often. And this was Nir and together with Amir Pnueli and Saar. And there they show that we can solve this game in cubic time, and tools have been built, and it's been used in robotics. But the downside, we've sacrificed expressiveness here. There are many things you cannot express in GR1. Now, I mentioned robotics at the beginning. And people usually don't build robots, expect them to last forever. Robots usually have a mission, okay? Go land on the moon, pick up some moon rocks, come back to Earth. You landed in Earth, you're done, okay? So same thing happened in business processes, okay? People have actually looked at insurance claim. how to automate insurance claim. The process can be very complicated, but you'd like to be paid eventually. So it's a finite horizon task. So in 2013, about 10 years ago, Giuseppe Giacomo and I said, let's look at LTL over finite traces. And so now some of the intuition changes. For example, always eventually P, which typically we think is infinitely often P, become no. In the final state, P must be true. That's what eventually always P mean on a finite trace. But there are lots of application. In fact, even before we came up with LTLF, Ona and I studied cost-safe LTL. We look at safety and cost safety. And cost safety is exactly the thing that looks at finite horizon in some sense. And people have been using this fragment of LTL to do with finite horizon LTL. So instead we said, let's just accept that we are living in a finite horizon world. And again, it turned out it doesn't help with words and complexity, but the algorithmics become quite easier. It become easier because we are back to a world which is much easier. We're dealing with deterministic finite set automata. Okay, and this is a world where we live much easier. In fact, classical area planning, you can think of it is given a DFA, is it non-empty? And the answer would be a sequence of word that will take a sequence of letter will take you from initial to finite state. That was classical area planning, because you're given a DFA, can you reach an accepting state? And now we can generalize it to the reactive case. It's become a reachability game. You're given a graph, and again, you're moving tokens between V0 and V1. But now your goal is not to do something forever, but to simply reach a final state. And this game has been studied actually in complexity theory, and they can be solved RP time complete. They can be solved in linear time. And so now we can kind of lift it to, if we have LTLF, we can translate it to DFA. And now we can play the game, the same game we played before with automata, but now we can play it on DFA, and we get a DFA game. And we're going to check realizability, and we can do synthesis all on DFAs. So let me just skip a little bit here. So, and we know how to translate it to DFA. And in fact, in experimental work, we use MONA to do it. We went from LTL to first order logic. And then we use MONA to give us a symbolic DFA. And then we can solve the DFA game symbolically. And we got a tool, SIFT. And just as a comparison, you can reduce LTLF synthesis to LTL synthesis, because you kind of say, well, there is some symbol that denote the last state of the trace. So you can encode everything in LTL, and we compare tools for leading tools for LTL synthesis with LTLF. And the answer was that, again, we can see that the scale much better. As the formula gets larger, LTL synthesis was just dying, and LTLF was scaling very well. So this gives us a whole new way to look at temporal synthesis. And again, based on the idea, yes, it took time in the worst case, but the algorithmic is much easier. We don't have to do suffer determination. We don't have to do with parity game. Everything is undergraduate course material in some sense. Okay, you can get undergraduate students play with it. It just let's push on the algorithmics, and in particular, this idea we can use what I call DFA technology. Can we go beyond LTLF? And answer yes, we can. For example, we looked at what we call the normal form for LTL, which is that you don't have until or eventually. Then you get a fragment of LTL that describe all safety properties. And it turns out if you have safety properties, then you basically, the complement of a formula is going to become essentially an LTLF formula, because safety property says bad things never happen. And the dual of this is going to be bad thing will happen eventually. So now we just flip the game. Instead of solving the game for the system, we solve it for the environment. And so we have another tool, safety SIFT, for this. And again, building on DFA technology, it scaled very well. And we have looked at, again, different way of doing it. Even we have looked at reducing it to SAT, because it turned out this can be reduced to Horn SAT, and Horn SAT is in linear time. So you have very good CDCL solvers. Still, using different technology beat everything else. And finally, even though we're dealing with a finite horizon games here, sometimes you do need to have infinitary assumptions. For example, if you want a message to be eventually received, you need some kind of an assumption that the channel must be up infinitely often. So even for finite horizon, you need infinitary assumptions. So we say, what happens if we take GR1 and combine it with a finite horizon specification? So we have GR1 assumption and finite horizon specification. And again, we get something that performs very well and beats LTL synthesis. So I've been calling this whole thing we've been playing now for decades the siren song of temporal synthesis. On one hand, it's a beautiful idea that we can synthesize program automatically, but complexity and algorithmics are very challenging. And infinite horizon semantics was very tempting because it seems very general, but we pay the price for it. And I think that one of the key ideas in computer science also is lower your expectations and accomplish more. Like model checking was kind of the same thing. It said, let's look at finite set programs. And there was derision when this idea came out. The people who do verification, whole verification, finite state programs, who cares? You're not doing real verification. And by being more modest, we've been more successful. And I think the same thing can be accomplished here. Thank you very much. We can take a quick question. There will be panel later, so we can have longer questions. Just quick questions, Raz?
I'm not sure it's so quick, so let's leave it for later.
Okay. Quick question. Anthony?
Okay, this is a very quick question, I guess. So you mentioned transducers, but do they appear in the finite?
Give him the mic.
So Moshe,
Yeah.
So you mentioned transducers in the infinite case. So do they also crop up in the finite case? No.
Yeah. You get a transducer. Mm-hmm. The game they are defined now, these are satellites that I skipped. There is always a question, who decides for finite horizon, who decides when the game ends? Okay. So in this case, our semantic is that the system decides when the game ends. You get to decide when the game ends. The environment has to play forever. You decide when the game ends. So in this case, the transducer also decides on the end of the game. This is a subtle issue. In fact, exactly how do you represent a winning strategy? Does it have a terminating state or not? That's the whole paper we wrote the whole paper just on that because it seems to make a huge difference in the complexity. I just don't have time to get into it here.
Okay, so in order to
move on, yeah.
In order to move on and stay on time, let's somehow go with, let's get the thank Moshe and go with after all the talk, we will have a short plan